Section 3.1 was all about the general characteristics of a scatter plot and how you describe two quantitative variables and their relationship. In 3.2, we're going to learn how you use a line of best fit to do a lot more in terms of analyzing quantitative data. So, first things first, we have a new vocab term for a line of best fit. In Algebra 2, that's what we would have called it, line of best fit. In AP Statistics, we use the phrase least squares regression line. It's the same exact thing as a line of best fit that you would get off your calculator. Why is it called that? We will learn that at the end of this lesson. I will frequently abbreviate least squares regression line as LSRL, and you can feel free to use that abbreviation as well. That's a pretty common one, least squares regression line. So just understand that that means line of best fit, and we'll talk later about why it's called that. What form will you see a regression line written in? In algebra and algebra 2, we use y equals mx plus b for lines. That's what you've done since you've been really young, beginning of your math careers. In AP stats, however, we use a slightly different format for lines of best fits. We actually use the format y equals a plus bx. And if you look on your formula sheet, this is what you're going to see, this basic format right here. Want to point out a couple things with regards to this equation. First of all, on the y, anytime you do a y in a line of best fit equation, a least squares regression line, you need to make sure you put a little hat on your y. This symbol is actually called hat, like a hat symbol. So this was pronounced y hat, which means the predicted y value. So the hat symbol means predicted y value. If you leave that out, you will lose credit on virtually every free response question involving lines of best fit. You have to remember the hat. That's a big deal in AP stats because you're using this line to make a prediction. It's not the actual promised y value for your points. So you gotta have the hat on that y. And when you write your equation right here, two things. First of all, you'll notice that the y-intercept, my plane number, is written first. That's intentional, and that's how you're supposed to write them in AP Stats. And the second part is the variable, and they actually use the letter b to represent the slope, which is probably a little trippy for you guys because you're used to b being y-intercept and m being slope. But this is the format that you guys should get used to using in AP Stats. Why do they mix it up? Why do something different? It turns out that we've talked about already how you can have more than one explanatory variable. You could have a second x in your problem, and it's easier if you have your x written second, because then you can tack on another explanatory variable. You could have like x1, you could have x2. You can tack on a third explanatory variable. It's just easier to do if they're all at the end like this. Having multiple x's, it gets into a concept called multiple regression, which is like a college stats topic. It's nothing we talk about in AP stats, but just realize that we write it this way so we can tack on other explanatory variables pretty easily. So get used to writing your linear equations in this format here with the plane number first. And the easiest way to lose credit on a regression equation is forgetting to define variables. You have to make sure that you define your x and your y when you do one of these problems. There's been at least one video where I've mentioned this already, but that's why sometimes you'll see it written where like you have the word from the problem, like miles or something like that, written in your equation, so you don't have to define it separately. So either do it with x and y and write off to the side, oh, x is this and y is this, or just use the word from the problem. Be careful with that because you will lose credit if you don't. So here's our big example for the video here. We've got a hypothetical AP stats project here where the students were shaking cans of soda. So they shook the cans for however long. I think that was consistent. Yeah, they shook them all for the same amount of time. And then they decided how long they were going to tap on the can to see if that made a difference in how much soda like bubbled out when they opened it up. So they wanted to see if tapping on the can made a difference in like it calmed down the soda, so not as much soda was left over. So their variables in this problem are how long you tap the can for on the X. That was their explanatory. And then their response variable is going to be the soda that is remaining in the can. So a higher soda content right here, this just says soda, which is less clear. But in the problem, it says that it's the soda remaining. So it might even be good to add soda remaining here. They have units on them, and that's all great. When they defined their variables here, they said y represents the predicted amount of soda remaining. There should have been a hat on this y, and please add that hat in your own notes right there. Y hat is the predicted amount of soda remaining, and x is the time that you chose to tap the can for. So over here at the bottom, they included our little equation. This is the equation for the least squares regression line. So we've got our line right there. You can see it does a pretty good job of fitting our data sets. And we can be doing some different things with our line of best fits to talk about features of this problem. So let's go on to the next page where I ask you for a few of those things. The first thing I ask you to do is to interpret the slope and the y-intercept of our regression line. This is going to be really important right here. I'm going to ask you to do this a lot on free response questions, and you can treat, you can treat both of those little things that we're about to write out as like scripts for our problem here. Sorry about that. Let me get back to my slide. All right, so interpret the slope and the y-intercept. We're going to treat these both as kind of like scripts that you can look at later. First off, our slope in this problem is the 2.63. I'm going to actually pause this for a second, then reformat and copy this down. So give me just a second right here. All right, so as I was saying, use these, like put a little star in your notes here so you have these written down as like scripts that you can use to model future problems on. Because it's very, very common to ask to interpret the slope or the y-intercept of a linear regression equation. So I recopied my equation up top right here, and I want to talk you through what each of these interpretations says. When we talk about the slope, try not to look at my answer yet until I talk you through it here. When we talk about slope in the context of a linear regression equation, we're talking about the guy on the x right here. And if you think about slope as a fraction, it's rise over run. So run is side to side, that's your x. Rise is your y. So for every 1 increase in x, your y is predicted to increase by this much. Okay? You would go up 2.63 over 1. So you just write about that in words, and this is like a little format for that. For every 1 additional second tapped, 1 additional increase in x, the soda remaining, that's y, is predicted to increase by the slope, 2.63. So basically, if I tap the can for 1 second longer, it's predicted that there will be an extra 2.63 milliliters left over. When you do these interpretations, the word predicted, you are going to forget it if you're not careful, and you will lose credit. You'll get only half credit if you forget that word. It's really important when you talk about interpretations that you include the word predicted. AP is very strict about that, okay? So it's predicted that our soda will go up by 2.63 milliliters for every extra second you tap it. And then the y-intercept is pretty much a similar thing. You guys should know that the y-intercept is when x is 0. So if you plug in a 0 for x, you'll just get this number for y. And that is a can tapped for 0 seconds. And it's predicted that it'll have this much soda left in it. So just think about this algebra style, but make sure you use the word predicted when you explain it. Problems can ask you to actually make predictions when they give you a value to plug in for x or for y. And this, again, is just algebra style. If they give me 10 seconds, that is an x. Make sure on problems like this that you show your work. If you don't show your work, you will usually lose credit. So show work for problems like this. And if you do that, you can just type this into a calculator. For that one, you're going to get 274.9 milliliters. So if you tap a can for 10 seconds, it's going to have about 274.9 milliliters. That's our prediction for the remaining soda. Okay? Nice and simple. Then I ask you to do something similar, but this time we're going to tap our can of soda for 60 seconds. And if you do the same calculation right there, you plug in a 60, you get 406.4 milliliters. Now, at face value, that's like, okay, yeah, that's my answer. And if you don't think that hard about it, it wouldn't seem anything out of the ordinary. My little question right here, though, should make you a little suspicious if you weren't already, though. How confident are you in your prediction? So let's go back for just a second and look at our data set right here. You always want to keep a close eye on your actual data points. I've got stuff everywhere right now. I'm just going to erase some of it, though, so we can see our picture a little better. If you look at the cans of soda in our experiments, the y values over here on this problem are all in the 200s. So the lowest y value that I have going on is going to be a 240 something, and the highest y value goes up to 290. We got a prediction of 400 for this can. So basically, I only tap my cans of soda for as many as 12 seconds right here. We tapped it for 60 seconds, and we're assuming that this same pattern carries on all the way to 60 seconds. That's a big leap right there when we only tapped cans from 0 to 12 seconds. In fact, a can of soda only has about 330 milliliters in it in the first place. So this 400 right there clearly isn't accurate because you're not going to keep creating soda as you tap the can. This pattern doesn't go on forever, and eventually it will stop when you reach the maximum amount of soda possible. Okay? So those two kinds of predictions. Our first one, when we plugged for 10 seconds, 10 is within the range of my data set right here. I had other values for x around it. 60 was way off from all my other points. Those are two different styles of predictions. We have what's called interpolation and extrapolation. And interpolation is going to be predicting within the range of other known x values. So that was like plugging in 10. I had already plugged in 8 and 12. So 10 was right in that range where I should feel pretty good about my prediction. But extrapolation is when you predict well beyond the range of known x values. And interpolation is going to work pretty well. Extrapolation, not so much. So you should avoid making extrapolations with data sets. Just like in our cans of soda, tapping for 60 seconds, it doesn't make sense that there would be 400 milliliters because you can only have 330 in a can. So be careful about making predictions way beyond the scope of the data you have at hand. So our other big concept for this video is the concept of a residual. And now we're getting into brand new territory where you wouldn't have seen this in Algebra 2. So a residual is basically a way of figuring out how far off our predictions were, or how far off our prediction is for a given data point. So a residual is a way of measuring how far off our prediction is for each can of soda or each person or each whatever we're talking about in the problem. And the way you actually calculate a residual, first of all, the symbol that we use for residual, like we don't have a dedicated symbol. I just usually write the word resid for residual. The way you calculate a residual in symbols, you're going to take y minus y hats. So that's how you actually calculate a residual, is your y value minus your y hats. Y is your actual y value, the one that belongs to the coordinates, and y hat is your predicted y value. So a good way to remember this, because I do not believe this is on your formula sheet right here, you're going to take actual minus predicted. To calculate a residual, actual minus predicted AP, you are an AP statistic. So actual predicted AP is a good way to remember that, okay? And basically, visually speaking, what a residual is going to be. So they ask us to calculate and interpret the residual for a can that was tapped for 4 seconds and had 250 milliliters remaining, they're asking us for the residual of this dot right here. A residual is going to be visualized as a little vertical line from your points to the line. This distance of that line right there is the residual. It's how far off our predicted line was from the actual value of the points. And you can have residuals that are positive or negative, just depending on where the point is with respect to the line. So how do you calculate a residual? Well, they tell us the can was tapped for 4 seconds and had 250 milliliters. Is this 250 an actual value or a predicted value? So think about that. The 250 is actually what happened for the can. That's the actual Y value. So this is going to be my Y, my actual. Okay? To find out the predicted value, I have to actually plug a 4 into my line of best fit. So if I plug a 4 into that equation, it's going to tell me what my predicted value is. And again, you want to get used to always showing that work for these problems here. So if I plug in a 4, I'm going to get out a 259.12. So this is my predicted Y, or my Y hats. So to calculate the residual for this point, I take my actual, which is 250, minus my predicted, which is 259.12. And if you subtract those, you get negative 9.12 for the residual. Okay? So calculating a residual is not very hard. You just take your actual Y value minus your predicted Y value. Now let's talk about what that actually means. I'm going to wipe some of this out right here so I have room to write down a little interpretation. But think about what that negative 9.12 tells us. A residual shares the units of your Y variable, because we were off on this problem by negative 9.12. So you can look at that negative 9.12 milliliters in 2 different ways, and either way is totally fine. You can say, well, I predicted 259, and I got a 250, so I'm about 9.12 below what I predicted. Or I could look at it in reverse. I could say that my prediction was 9.12 above what it actually ended up being. Either of those ways of interpreting it are totally fine. So let me go ahead and write something out for that. The predicted, let me think how I want to do this here. I think because it's a negative value, it makes more sense to talk about it being below. So I'm going to say that the actual soda remaining for this can was 9.12 milliliters below the value predicted by the LSRL. So the actual amount of soda, 250, is 9.12 below what the line of best fit thought it was going to be. That's all a residual is just how far above or below you were from the predicted amounts. You can interpret it this way. It wouldn't be wrong to interpret it in reverse and say that the prediction was above the actual value, but I like to keep it consistent. If it's a negative, I think below. So I interpret it in that way. Either way is cool though. So residuals are not that bad, even though they sound kind of sophisticated. They're just talking about how far off you are. And the last thing I want to do in this video right here is give you an idea of where that term least squares regression line comes from. When you look at a line of best fits, you want to make that line of best fit, and this is just a new context right here, random problem. We want to make it so this line of best fit is tilted so these little residuals right here are as small as possible. We don't want to be off by a lot when we make our predictions. So depending on how we tilt that line, some of our residuals might get bigger, some might get smaller, but we want to make it so the cumulative amount that we're off by is as small as possible. Say I took all these residuals though, and I just added them together right now. I added up all my positive guys and I added up all my negative guys. As you might guess, what's going to end up happening, just like we did with standard deviation, similar idea. They're going to wash each other out. The positives and the negatives are just going to cancel each other, which is no good. So just like with standard deviation, what we end up doing is squaring our residuals so they're all positive quantities. Visually on a graph, you'll see pictures like this, where basically to visualize squaring that quantity, they'll draw like a literal square on the picture like this. To square this guy, they'll draw a square like this, etc., etc. So points that are close will have small squares, points that are far away will have bigger squares. So this is just visually showing the squared residuals. What we're looking for is the sum of the squared residuals to be as small as possible. So it's called a least squares regression line because we want the area of all of those squares to be as small as possible, because if that area is small, it means that our line is doing a good job making predictions. So that's why they call it an LSRL.